I want you to imagine, just for a second, a world where every single safety alarm in an industrial plant is armed. Like every single pressure sensor is just perfectly calibrated.
Right. The whole system is completely locked in.
Exactly. Every pre-flight checklist has been thoroughly ticked off. The multi-million-dollar monitoring system is humming along without a single glitch anywhere.
It's the ideal scenario.
Yeah, but here's the thing. Despite that absolute perfection, disaster still strikes. The system was flawless, but it failed anyway. And, you have to ask, how is that even mechanically possible?
Well, it is this profound engineering paradox, really. You design what you believe to be an impenetrable defense, and then it just gets bypassed entirely.
Yeah.
And it's not because the technology broke down.
Which is wild. And we are getting right into it today on the deep dive. So we've got our hands on a highly confidential draft press release from a company called EON AI Ventures.
Which is a fascinating document.
Oh, it really is. It's dated August 11, 2026. But what makes this so unique is that we are looking at the raw, totally unedited document. I mean, it still contains all the internal hold conditions at the bottom.
Right. Those notes are usually scrubbed.
Exactly. They're the direct notes to the PR team and the legal department, outlining exactly what cannot be changed or, softened before the document goes public.
And looking at those raw notes, I mean, it gives us an unfiltered view into their actual strategy, but more importantly, it exposes a massive blind spot in modern industrial safety.
Totally.
And to understand why this matters to you as the listener, we really have to start with the sheer scale of the data EON is working with here.
Because it's not a small sample size.
No, not at all. They didn't just model theories on a whiteboard. They analyzed 40 years of official government pipeline accident reports. We are looking at an analysis of 21,386 individual incident reports, and that dates all the way back to 1986.
Yeah, when you look at an industrial accident, say, a pipeline bursts or a massive refinery has to shut down, the automatic assumption is always about the hardware.
Right. We want to know what snapped.
Yeah. We immediately ask what part broke. We assume a valve snapped or a sensor just randomly stopped transmitting data.
Well, because that is how we are trained to think, right?
Yeah.
We want to find a physical, tangible failure to blame.
But EON asked a highly counterintuitive question. They looked at those 21,000 plus incidents and asked, well, what was the safety equipment doing at the exact moment of failure?
And the answer is pretty uncomfortable.
It really is. The data reveals that the safety equipment was overwhelmingly working.
It was functioning precisely as engineered. I mean, it just didn't matter.
I have to admit, I genuinely struggle to wrap my head around that. Like, how can the safety system be working perfectly if an explosion is actively happening?
It sounds impossible until you dig into the numbers.
Yeah, so let's look at the specific statistics in this draft. You picture a modern control room, right? You've got glowing screens, endless data feeds, operators watching 24/7.
The nerve center of the whole plant.
Exactly. But according to EON's analysis, the control room spotted the problem only 24.3% of the time.
Wow.
Which means 3 times out of 4, a human being on the ground, literally sometimes just a member of the public walking their dog, noticed the disaster before the multi-million-dollar system did.
And you have to remember, those monitoring systems were active. They were recording at that exact time. The data was flowing.
The inspection data is even harder to square, honestly. 63.4% of pipeline failures happened within 2 years of a professional inspection.
That is staggering.
Right. A quarter of them failed in the exact same year they were inspected. The pipe was analyzed by professionals, given a totally clean bill of health, and it failed anyway.
What's fascinating here is that we are looking at a fundamental misdiagnosis of where risk actually lives.
Say more about that.
Well, consider the excavation data they included. There's a universal rule in the industry: before you dig near a pipeline, you phone a central registry to get the line marked. It is supposed to be this foolproof, totally locked down system.
Yeah, call before you dig. We see the signs everywhere.
Exactly. Yet 63.3% of the times a line was hit by an excavator, the digger had in fact phoned first. The rules were followed, the line was marked on the ground, it got hit regardless.
Okay, but what about corrosion? Because that's just rust. It's the slowest, most predictable, most chemically visible way a pipe degrades.
You'd think we'd catch that every time.
Right. But ERN found it is the least detected cause of all. It's caught only 13% of the time. I just don't understand how data that obvious just gets missed by everyone.
Well, because the failure isn't a lack of data. As the draft puts it so well, the pipe was inspected, the ticket was raised, the alarm was live. The core issue is fragmentation.
Fragmentation, okay.
Right. You have four perfectly correct pieces of data, but they exist in complete silos. The pressure sensor data is in one system, the inspection schedule is on a different server, the maintenance log is sitting in a third software package somewhere.
And the shift roster is just on a clipboard in the break room.
Exactly. No single intelligence is pulling those four isolated facts together to ask the crucial question, which is, what does this specific combination mean for the shift starting right now?
Okay, so it's like having a state-of-the-art home security system. You've got the motion sensors in the hallway, you've got the 4K cameras on the porch, you've got laser tripwires on the windows.
A total fortress.
Right. The system is functioning perfectly.
Okay.
But you leave the physical front door wide open when you go to work. It just doesn't matter how high definition your cameras are if the system isn't designed to recognize that the most critical barrier is simply sitting open.
Yeah, that is a very accurate way to visualize the disconnect.
So if the sensors are doing their job, we really have to figure out what is actually causing the failure. And that requires looking at the lifespan of the equipment itself.
This is where the data gets really revealing.
Yeah, because when EON sorted those thousands of incidents by the age of the equipment at the time it failed, the data didn't just plot out on a smooth, normal curve. It split into two radically different categories.
It creates a stark divide in how things break down. So category 1 encompasses what we might call the slow puncture.
Go.
This is when the pipe or the weld gives way over time, which typically happens at a median age of 51 years. Or it's corrosion eating through the metal, which happens at around 43 years.
So these are long timelines.
Very long. And these failures are highly predictable because they obey the basic laws of physics and chemistry. You can track their degradation over decades with the right tools.
But category 2 operates on a completely different timeline, like entirely different.
Category 2 is your unlocked front door. This is when the mechanical equipment itself just fails, which happens at a median of only 8 years.
Well, 8 years compared to 50.
Right. But even more critically, this is when somebody operates the equipment wrongly, which happens at a median of just 7 years.
7 years.
Yeah. These are incredibly fast failures. You might get days or weeks of warning if you're lucky, but often you get zero warning at all. There is no instrument currently invented that will tick upwards on a gauge to warn a control room that a tired technician is about to turn a critical valve in the wrong direction.
Okay, let's unpack this. Because if I look at the industrial safety market right now, almost every single AI startup and predictive maintenance tool out there is obsessively focused on category 1.
Oh, entirely.
They're all building these advanced algorithms to predict the slow, physical breakdown of metal using vibration and acoustic sensors. Are they essentially just searching for their lost keys under the streetlight because the light happened to be better there, while completely ignoring the dark alley where the immediate danger is actually lurking?
That is exactly the dynamic at play. I mean, the industry builds tools for the problems that are easy to quantify.
Right, the math is easier.
Exactly.
Yeah.
It is mathematically straightforward to measure pipe thickness or to analyze the frequency of a vibrating bearing. It is incredibly difficult to measure human fallibility.
But if sensors can only catch those physical breakdowns, we're left with a massive blind spot, which is the human being actually operating the machine.
Which is the biggest variable of all.
Yeah, and why do highly trained, deeply experienced professionals make these catastrophic errors? The EON document uses a very specific scenario to explain this, and I think we really need to walk through it.
Yeah, they focus on the pump seal replacement procedure.
Right, so imagine a technician at a refinery, and they are tasked with replacing a seal on this heavy-duty pump. It's a complex, grueling job. It has 26 distinct steps and takes up the entire morning.
It's hard physical and mental work.
Exactly. So the tech works through the checklist, sweating, doing everything right. They finally reach step 23. The pump goes back into service, it fires up, it's humming perfectly. The primary goal of the morning has been achieved.
And from a psychological standpoint, the job is done.
But physically, there are still 3 steps remaining on the written procedure. The tech still needs to bolt the physical safety guard back over the coupling. They need to reconnect the electrical earthing strap, and then formally close out the work permit in the computer system.
But routinely, those last 3 steps are just skipped or completely forgotten.
In EON's draft, emphasizes this heavily. This isn't negligence. This isn't just a lazy worker cutting corners.
No, not at all. It is the most heavily researched cognitive error in 50 years of safety science. It is officially called the post-completion error.
Post-completion error.
Yeah, right. When you achieve the primary goal of a complex task, your brain experiences a shift. The working memory essentially clears the cache. The overarching objective has been met, so any ancillary steps that follow the primary goal simply evaporate from your immediate consciousness.
It's exactly like going to an ATM. Your entire primary goal is to get cash. The machine dispenses the bills, you grab them, your brain registers mission accomplished, and you just walk away, leaving your debit card sitting right there in the slot.
Yes, that is the perfect everyday example.
Or like making a photocopy. You grab the fresh copies you wanted and completely forget the original document sitting right there on the scanner glass. The brain just drops the context entirely.
And what's critical to understand here is that while leaving your card at the ATM is, a huge inconvenience, leaving an earthing strap off a high-pressure pump in a combustible environment is a fatal risk.
Yeah, that's a whole different level of consequence.
And no vibration sensor in the world can detect an absent earthing strap. To predict a post-completion error, a system would need to understand the structural layout of the job, understand the physical equipment, and practically be inside the worker's head.
Wait, I need to stop you there.
Yeah.
How can a piece of software possibly know that I am going to forget step 24 on a specific pump before I even put my hard hat on? I mean, that borders on science fiction. Is this AI just guessing based on broad industry averages?
It's not guessing at all. It's structurally analyzing the environment and the procedure itself.
Yeah.
EON AI Ventures introduces a new model here called EON Delta.
Okay, EON Delta.
Yeah, and they approach industrial risk by breaking it down into 3 distinct layers. Layer 1 is metal wearing out. Now, EON freely admits other companies do this well, so they just integrate existing sensor data for that.
Smart. Don't reinvent the wheel.
Right. Layer 2 is a person missing a step. And layer 3 is a safety defense quietly rotting like an alarm that gets disabled for routine maintenance and never toggled back on.
And the draft notes that massive disasters rarely stem from just one of those layers failing. It's when 2 or 3 of those layers align on the exact same Tuesday afternoon shift that a facility actually explodes.
Precisely. So how does EON Delta predict the human element? It doesn't scrape the open internet for generic safety tips. EON's AI uses natural language processing to read a company's own written work procedures. It literally digests the PDF manuals that the workers follow.
But reading a manual doesn't predict an error. Like reading the recipe doesn't mean you know I'm going to burn the cake.
It does when the AI is trained to recognize the psychological triggers of an error. The AI maps the procedure and flags specific structural weaknesses.
Oh, I see.
Yeah, it looks for steps that immediately follow a natural interruption. It scans the verbs for actions that provide no physical feedback, meaning there is no audible click or tactile resistance to let the worker's brain know the step was actually completed.
That is wild.
It also flags steps that undo a previous action, like remembering to turn a valve back on that you turned off 3 hours ago.
I see. So it's analyzing the actual design of the task itself to find the traps.
Exactly. And then it layers that with situational context. Is this worker at the end of a grueling 12-hour night shift? Has this specific step been skipped safely in the past without consequence, which creates a false sense of security? Are any backup barriers on that equipment currently logged as out of service?
It's pulling all that together.
Yes, and if we connect this to the bigger picture, it fundamentally changes how risk is managed. The plant supervisor doesn't get an investigation report after an incident happens. They get the procedure marked up with psychological weak points before the shift even begins.
It's a brilliant concept, but logically I am stuck on the implementation.
How so?
Well, how does a tech company in California force a blue-collar worker out on a rig in the North Sea to carry an AI tracking device without them feeling like corporate is micromanaging their every single move? If the workers hate it, the data is going to be garbage.
That is the exact logistical hurdle that destroys most industrial tech startups, frankly. But the EON document reveals a very clever Trojan horse strategy. EON doesn't hand them a new tracking device to carry around. EON already manufactures the rugged handheld devices that workers use daily for training simulations, digital manuals, and step-by-step technical guidance.
Ah, so the hardware is already in their pocket.
Exactly. The workforce already relies on and trusts the physical hardware. The predictive AI is simply a new software layer introduced into an ecosystem that is already deeply embedded in their daily routine.
That makes a ton of sense. But for an AI to actually be predictive, it has to be trained on historical data. It has to learn what a failure looks like before it happens.
It needs a baseline, yes.
And this brings us to a four-step process
Mhm.
EON outlines in the draft. And step 4 highlights this massive flaw in how standard AI operates today. So step 1 is read the procedure. Step 2, add the context. Step 3, give the warning. But step 4 is, quote, watch what happens. And EON is currently trying to patent this specific mechanism.
Because step 4 solves a hidden data corruption issue that affects literally every other predictive system on the market today.
Explain that, because when I read this, it completely changed my understanding of machine learning in the physical world. Because in a working industrial plant, most warning signs like a weird vibration or a tiny pressure drop, they never actually turn into a reportable accident.
And why is that? Because a human operator notices the anomaly, grabs a wrench, and quietly tightens the valve.
Right. And they don't log it, they just fix it and move on with their day.
Yeah.
So what happens when a standard AI model ingests that historical sensor data?
The standard AI looks at the timeline, it sees a dangerous pressure anomaly appear, and then abruptly, the anomaly just vanishes. The system normalizes.
But the AI doesn't know a guy with a wrench fixed it.
Exactly. Because the human intervention was never recorded in any database anywhere, the AI confidently deduces that the mechanical system just self-corrects. It learns that these specific pressure spikes resolve themselves magically and are therefore not a threat.
It literally trains itself to ignore the exact warning signs of a failure.
It is a profound form of survivor bias. The AI is essentially marking its own homework using an incomplete data set. But because EON's device is physically in the worker's hand at the point of action, it logs the intervention.
It closes the loop.
It captures the reality that a human fixed it, or that a human actively chose to bypass a step due to a time constraint. Capturing the reality of human intervention cures the AI of that dangerous survivor bias.
Which explains why their competitors can't simply replicate this. I mean, a company making acoustic sensors has incredible machine data, but they have zero visibility into the human deciding to skip a step.
Right.
A digital checklist company have the tablet data, but they don't have the physics models of the equipment. EON has the interface, the physics, and the behavioral history all integrated together.
They have built an architecture at the precise intersection of human psychology and mechanical reality.
Here's where it gets really interesting, though. When you start talking about recording every granular action a worker takes and feeding it into an AI, corporate lawyers usually shut the conversation down immediately.
Oh yeah, the liability is huge.
Companies are deeply paranoid about their proprietary procedures leaking into a global machine learning model.
And legally, they have to be. Two competing energy firms cannot share their operational vulnerabilities or their facility blueprints. That's a non-starter.
But the draft tackles this privacy issue directly. EON uses a structure where a specific facility's data, their unique manuals, their equipment layouts, their specific errors that never leaves their local server. The customer owns the local model outright.
But there is a broader learning happening.
Right. However, the AI learns generalized psychological patterns. For instance, the AI learns that human beings globally tend to skip step 24 if they are interrupted at step 22. Those anonymous behavioral parameters are updated across the global network.
It's very smart.
So every client benefits from the psychological insights without exposing a single line of proprietary code.
It is an elegant use of federated learning. But, for all the sophisticated architecture we are discussing here, as you read through this leaked document, the most surprising element isn't the technology they are unveiling. It is what EON AI Ventures explicitly refuses to claim.
Yes, Section 6 of the draft. It is literally titled, quote, "What EON AI Ventures is not claiming." You read it, and you have to do a double take.
It's jarring to see in a press release.
There is absolutely no accuracy percentage listed in this announcement. They openly state that EON Delta has not been fully trained, it has not been tested in the real world, and there isn't even a pilot program running yet.
This raises an important question regarding corporate integrity, particularly in the current AI landscape. We are entirely accustomed to tech companies promoting vaporware.
Oh, constantly.
Promising 99% efficiency on algorithms that haven't even been coded yet.
We see it every single day.
Yeah.
The magic AI that solves everything instantly.
But EON adopts the inverse strategy. Rather than fabricating a performance metric for the press release, they are publishing the grading rubric for the test they intend to take.
The shift test.
Right, they call it the shift test. It is a methodology where you feed an AI only the fragmented data that a supervisor actually had access to at the 6.0 a.m. shift handover, and you evaluate whether the AI can accurately flag the vulnerability that caused the accident at 2.00 p.m. EON is publishing these rules publicly so anyone can run the test.
So what does this all mean? When you scroll down to the internal hold conditions at the bottom of the page, the notes the PR team is supposed to delete it become so clear.
Those notes are the best part.
The internal memo aggressively demands that Section 6 must not be shortened, it must not be softened, and it cannot be buried at the end of the document. The note literally says, quote, "It's the only reason a journalist can trust the rest of the document."
It is a radical commitment to transparency. They are presenting the current fragmented state of industrial safety, proposing a deeply researched hypothesis, and providing the exact framework by which regulators and competitors can hold them accountable when the system actually goes live.
The legal notes even require that lawyers verify all patent filing dates and ensure that the back-end software proving their 40-year pipeline analysis is publicly accessible before this text is released.
It's completely watertight.
It's a masterclass in show, don't tell. They are practically daring the industry to audit their data.
And by refusing to participate in the standard hype cycle, they really force the market to engage with their core premise seriously. And their premise that human cognitive limitations are the actual frontier of industrial safety is completely substantiated by decades of incident reports.
It completely shifts how you view failure. And that is exactly why this matters to you, whether you are managing a high-stakes engineering project, running a corporate department, or just trying to keep a busy household functioning.
It applies everywhere.
Realizing that mistakes often happen not because we are careless, but precisely because a task feels finished. That post-completion error is a critical insight for how we structure our own daily workflows.
It requires us to acknowledge that our brains are not always reliable narrators at the end of a process. We are biologically hardwired to mentally clock out the exact millisecond a primary goal is achieved.
Which is a little scary when you think about it.
It is, which leaves us with a compelling question. If our neurological architecture naturally drops the context once the main objective is met, how many of our daily frustrations and accidents are actually post-completion errors in disguise?
Oh, wow.
Think about the fender bender that occurs right as you pull into your driveway because your brain signaled, hey, we are safely home, or hitting send on a crucial email but forgetting the attachment because clicking reply felt like the job was done.
I do that all the time.
We all do. And if an AI model like EON Delta can be trained to predict these psychological blind spots in a highly complex refinery, how long will it be until algorithms begin predicting and correcting the post-completion errors in our everyday lives?